Alright, today we're moving on to Concept F. We're going to be focusing on how to calculate cell voltages in voltaic cells that we learned about in the previous concept. So here's just a rough diagram of a voltaic cell. Remember, we have our anode, which is assigned our negative electrode, and zinc is higher on table J, which is a hint that this is where, oxidation is going to occur. We can also see that by the half reaction. Electrons always travel through the wire. There would also be a voltmeter along this wire to record the voltage, which is what we're going to be calculating today. And then those electrons travel over to the cathode where reduction is occurring for copper. Remember, this is assigned the positive electrode, and copper is also lower on table J. And we can also see by the half reaction at the bottom that reduction is occurring. So we're going to actually be looking at how to calculate the voltage that is going to occur in various half cells. And we're also going to do a lab on this, so this is leading up to that. Now, in order for this voltaic cell to work, there has to be a tendency for species to attract electrons more than another, which we know by using table J which one is going to be able to attract those reduced compared to what's getting oxidized. The tendency for a species to gain electrons in a redox reaction is measured in volts, and this is a basic unit of something called an electromotive force, or EMF. Now, voltaic cells, this is a battery. The anode is the negative terminal where the electrons flow out, and the cathode is the positive terminal where electrons flow in. That's why if you flip around the batteries in a device in the wrong direction, it's not going to be able to work because those electrons aren't able to flow through the device in the correct manner. Now, the voltage you calculate is going to be the initial voltage of the cell. As the cell is used, the voltage will decrease as the reactants are used up. When the cells reach equilibrium, the reactions stop, and we say the battery is dead, and that's when your device stops working and you have to change out the batteries. Now, how good is a battery? This depends on the amount of charge it can transfer. Its voltage, which is considered the potential difference, is measured in volts. So how do you calculate cell voltage? Well, just like we've done in the last few units, is you're going to be writing the oxidation and reduction half reactions that are occurring in the cell. You're going to assign the reduction half reaction the voltage listed on the chart. So I'm going to be providing you a chart in class. This is one line of that. Okay. The copper plus 2 is the species that's getting reduced. And you can see that by how it's gaining 2 electrons. So your focus, when we assign the reduction half reaction voltage, we're focused on the one that's written on the left that will get paired up with the reduction potential, which here is a positive 0.34 volts. Then you're going to assign the oxidation half reaction, which is the negative or opposite of the voltage listed on the chart. The voltages listed on the chart are always reduction potentials. So for these oxidation potentials, we have to just simply reverse the sign from the table. So for the reduction of Cu plus 2, which would be the reverse of this reaction where Cu solid is forming an ion plus the 2 electrons, we have to flip this sign. So for this, again, this reaction you see on your screen, the voltage would be negative 0.34 because this is the oxidation of that reaction. And then we're going to simply add the 2 voltages together. This gives us a net voltage or overall voltage, and we're going to go ahead and calculate that for potassium and gold. So potassium is oxidized, and if we look here, we can find K, 3 from the bottom, where because it's getting oxidized, and here again this is a reduction potential, we have to flip the sign. So instead of negative 2.92, it's going to be a positive 2.92. We also have gold that's getting reduced. So right here we can see that we have our gold's half reaction. It is getting reduced. So we're not going to flip the sign. We're simply going to copy it directly down from the chart. So 1.5. Okay, then we're going to take our net voltage, which we're simply going to be adding up the 2 together. So you get a voltage of 4.42 volts. And then just to review, remember, this would be our net ionic equation. This is basically the sum of the 2 half reactions once we have balanced out the electrons. So how do you calculate cell voltage? In terms of knowing if this reaction can actually happen, we can apply it. So if the voltage is positive, the reaction we can say is spontaneous. It happens on its own, which is what we need to happen in a voltaic cell. However, if you do calculate a negative voltage, the reaction is non-spontaneous. And we'll be applying that to our lesson tomorrow on electrolytic cells. So what is the potential difference of this reaction? Remember, we're going to first assign oxidation numbers to all the elements above. We're going to write the half reactions. So you can see that zinc is going from 0 to +2. Remember oxidation, which is the loss of electrons. Those loss of electrons are on the right. And then reduction is the gain of electrons, in which copper is going from +2 to 0. So now that we have our half reactions, we can use the table to figure out their volts. So for oxidation, remember, was for zinc. Now remember, oxidation formula or equation is the opposite of our reduction one that is going to be found on the chart. So remember, because it's for oxidation, you're going to simply flip the sign to positive. 0.76. Copper, which is reduction, is going to be found on this line where you have positive 0.34. Okay, so your half reaction should match what's in the table to leave the sign the same. However, if it's oxidation in which you have to flip this equation, you also flip the sign. So to determine the cell voltage, we're going to add the two together and find that it's 1.1 volts. Because this is a positive voltage, the reaction is spontaneous. So this is the cell potential, or I should say initial cell potential of our cell. Okay, so we're going to apply this to a lab directly and do a little bit more work on this tomorrow. Also make sure you review voltaic cells. They're incredibly important for this unit, so you might want to go back right now and look that over. All right, you don't need any summary or quiz, so you are all set.